Thank you very much for inviting me to the seminar today. I'm Klimis, and I've been supervised by Dr. Bowell and Janine Ilian from Math and Stats department. I also go supervised from Cell Research from Wayne Johnson, Kieran Gilbert. So I'm a third year PhD student in Math and Stats, and of course discipline is in statistics, but my title is forecasting the electricity price with wind renewables in electricity markets. So in today's agenda, I will present to you the latest developments, research developments, etc., that we try to combine electricity price forecasts and wind power forecasts in order to draw insights about future movements for the price and all of that. This is not finished yet. It's on a very early stage. But I will go through the models and you will see what is going on exactly. So what is the motivation behind that is the increasing uncertainty in the electricity market. So you expect that wind power is intermittent, so it's volatile. So because of this, you will have increased volatility in increased markets, especially in the Great Britain. That wind power is it's growing every day. Okay. The other thing is that we need to use the forecast as information signals. So what is information signals? Okay. So there is a two-sided motivation about that. It's first of all is the financial motivation, of course, for the market participants to adjust the position better and make use of the wind power better. But on the other hand, this will help the grid be more stable and to be more green. And of course, the other thing is that the most challenging thing is to model this volatility in the price imbalances. So in the Great Britain, we have three major markets: the day-ahead market, the intraday market, and the imbalance market. Well, some people they're saying balancing mechanism. Okay, that's the same thing. So you will see something that we include prices from all these three markets in order to build our models. The other book that I like it very much, we construct that with my colleague. So you see here the evolution of wind power capacity in Great Britain and a glimpse to the future as well. So we collected data from the Crown State Open Data Portal and the Energy Pulse. And fortunately, we have data for the offshore plants to now. We do have some data for onshore, but I'm not persuaded yet that they reflect the truth. That's why you don't see after the 2024 any data for the onshore. So you can see the increasing capacity for the next year. So we will have more volatile power energy in the future. So we need to be very proactive for the next years, and we need to build our methodology and the knowledge behind that in order to tackle those moments that we are waiting for the future. And of course, the 2030 is the net zero. I don't remember. They're changing that every day. So yeah. So as I told you that we have two models here, two forecasting models, and we are using those forecasts that we are using those two different forecasts that we have in order to see what's going on. Okay, the first one in the electricity price forecasting, we are using, of course, public available data from NISO. So I will provide you a summary. What are these public features that we are using? We're using features from IPEX day-ahead market, and these features are available for my research only. This data has been bought from us, and the intraday market as well. Okay, this is about the electricity price forecasting model. The second wind power forecasting, we're using wind speed forecast from the ACMWF, and we implemented a wind to power model. And this is the step 3 that we are at the moment, that we try to, first of all, make a joint analysis of our forecast that we are getting. And of course, after that, we anticipate to fit a model in order to make use of those two forecasts. And one can ask, okay, why you're not building a forecasting model about the electricity price and happy days? So the general idea on this is that we want to incorporate the updated forecast of the wind power generation to the price, because we are strongly believe that the update on the forecast that the market participant have, the data on the wind power forecast, will help to adjust their positions better, okay? Because wind power is more cheaper than the fossil fuels, okay? So you expect that we have wind power forecasts available in multiple lead times as we are approaching the time that we want forecast, okay? So, don't expect to see much of AI or deep learning or something like that. So I'm just focusing more into feature engineering, of course, and modeling. That we are using state-of-the-art models, and of course, we have a proposed model that we built by ourselves as well. So here you see the general this time series that we are using. Okay, so it's very late data that we could have access to those. So we're using as a training data set from 2020 till the end of 2021. As a validation set, we are using the whole year of 2022, and we are producing forecasts of 2023. Okay, you observe those hiccups in the time series, okay? Okay, so I need to remind you that during this time, we have the Ukraine war and the COVID period as well. So these hiccups here, reflecting those moments, okay? And on the other hand, in the price domain, it's a bit difficult to characterize these spikes sometimes, because a lot of things can happen during those moments. Okay, maybe you can have the Ukraine war. Okay, maybe you can have COVID. Maybe you can have market participants that they have huge capital and they're bidding high all the time. You can have many things. Okay, and some things, of course, you don't have the information behind that in order to create information features. Okay, that's why we are including information from all the markets in our price model, because if market participants did not participate in the day-to-day market, they will hold their position to go to the bounce market or to the intraday. Okay. Having that said, let's go to the feature engineering that we did with Zero. So, first of all, we acquired the executed orders of the intraday market. So the executed orders from the intraday market are volumes, that's orders that there's going to volumes and prices that they can put anytime, 24/7, anytime, for a specific time in the future, okay? And this has been executed. So we have the information that this order has been executed already. So this data that we acquired in the first round, it's a massive beast, I would say, million rows. So irregular data, okay? As you can see, individual trades, irregular timing, high variance in the volume of trades. You don't know what the appetite is behind that. So not appropriate data for regression methods, okay? So what we did, we tried to fix the time step in the feature that we will create, okay? And then we said, okay, we need to incorporate the volume as well, okay? So we use the volume weighted average price, Okay. The other thing that we incorporated is the price trend. So imagine that before the time that we are forecasting, we fit a simple linear model to the volume weighted average price that we have in the period of 2 hours before the time that we create the forecast. And we find the intercept, so we say that this is the trend. Okay, we incorporate that as a feature. And of course, having all the volume weighted average price, we can create an empirical distribution and we can extract specific quantiles to see the dispersion in specific time durations before we produce the forecast. So we made the best that we can do to draw information from the raw data. Okay. So the next one, I know I come from math and stats, so you will see some mathematical notation. Sorry for that. So here is the price spread model, and because I said that we're incorporating prices from the intraday, the balancing mechanism, and the day-ahead market. Here, our target variable is the difference between the imbalance price and the day-ahead price. Okay, that's what we are calling price spread. You need to remember that day-ahead market is the most liquid in the Great Britain. Okay, sets a marginal price all the time for the electricity markets. So that's why we create this difference between the imbalance price and the day-ahead price. And we're incorporating the features that we created from the intraday to our model. And of course, we have the public predictors as well extracted from NISO. So I will go through the various terms that you see here, and I will explain, I will try to communicate with you what we're including. So the first term corresponding to the volume weighted average price, okay? So for the previous and current, and I will not say much because one that is familiar with forecasting, it's simple that we're incorporating lags of this. But most of the times I get a question about the future. What is the future? Okay, you don't know the future. Okay, I need to make a comment about this. So imagine that we are releasing a forecast on time t, for example. Okay, and you have executed orders that they're responding to the time plus one that we try to make the forecast. Okay, but you're releasing your forecast empty. So you can have executed orders on time -1 that they're responding to future settlement periods that you can forecast on time +2, time +3. Okay, but you already have the price for executed orders that they're responding to future settlement periods at the time that you're forecasting. Okay, so we are incorporating this price as well. Okay, if you're familiar with the term neighboring prices, okay, because we have executed orders or executed contracts, if you want. So as I said, we incorporating the dispersion, of course. We're incorporating the trend, the intercept, and of course we have a range of public predictors. The public predictors here is the forecast demand provided by NISO, is a day-ahead margin. Of course, we have interconnector imports and exports of energy, solar forecast as well. We're incorporating solar as well, and also we're incorporating the settlement period dummies. Yeah, I forgot to tell you that the granularity of our data is half-hour frequency. So you expect 48 settlement periods per day. And the other term, it's the informatic missing predictors. I want to stay for that for 1 minute and say to you that you don't expect the intraday market to have executed orders in every time step that you're exploring. Okay, sometimes you cannot have orders, executed orders. Sometimes market participants, they don't put orders, they don't, they bid on the day market. I don't know. You don't know. So you can understand that we have a lot of missing values from the features that we derived from the intraday markets. So what we did for that, we used a methodology from biostatistics that you create a vector for each covariate that will mark if you have a missing value or not with simple 0 and 1. So we created vectors responding for that. So you expect in the end that we have a very large table in the end, a lot of features. So you expect those features and vectors that they're telling if we have a missing value or not in the intraday features. Okay. So we are producing probabilistic forecasts. Okay. And we are producing probabilistic forecasts for 50 minutes ahead, 30 minutes ahead, and 60 minutes ahead. Very short term. Okay? Because for good yeah, it's for 2023. Okay? And we want to make this very short term because we believe that can be used from traders in order to adjust the position online. Okay? The models that we used. Here. So what we said that okay, so we will incorporate approaches that our predicted distribution follows a fixed standard deviation, and we will incorporate approaches that will have dynamic variation as well in our predicted distribution. So the first one, we used linear regression with lasso. So penalizes parameters. So penalizes symmetrically the predictions. Okay, and how we create the predicted distribution in this case, which is a fixed case. So we produce an estimate. Okay, and this is the mean of our predicted distribution, and we compute the standard deviation from the in-sample residuals. It's a parametric way, and you need to make assumption that your predicted distribution follows a specific family. Okay, a lot of limitations. The other one is that we said we found out that the price spread has a strong connection with the grid when is a deficit or surplus of energy. Okay, so we created a mixture model. Okay, two models, for example. Okay, conditional to the grid to be surplus or deficit. Okay, and we combine those both models with lasso again, fixed again. The MMNG boost is the non-parametric way. This is when sorry, is a parametric way. My bad. Sorry. The MMNG boost is where we use a boosting algorithm in order to create our mixture model. The same goes here as well, conditional to the grid to be deficit or surplus. But here, we are predicting the standard deviation of our predicted distribution in every time step. It's dynamic. Okay? And of course, we use quantile regression because quantile regression, it can be, it's named as state of the art in our case in the electricity price. Quantile regression models won a lot of forecasting competitions in the past. JEFCON 2014, if I remember right. So we have here the QR benchmark model, which is it's a benchmark model that we don't incorporate any intraday features. We're using all the other features, but not intraday. And we do this because we want to show the power, the forecasting accuracy and the power that we can get from the intraday features. Okay, this is the main contribution here. And the QRLSU is that including all the features, the intraday features, and all what you saw, but penalized again with a LSU parameter. Okay, and as you can see in the first row is the mean p-bar loss. This is the accuracy metric that we are using in the probabilistic forecasting, that we can assess our model in different probability levels, the accuracy, the quantile loss. Okay, So the quantile loss, for the people that they're not very familiar, imagine that you have mean absolute error that it's used all the time. Mean absolute error is symmetric, okay? But in quantile regression, it's like you having a mean absolute error penalized differently across probability levels. So for example, in probability of 10% or 0.1 quantile, if I predicting above the quantile, has different penalization if I'm predicting above 0.9. Okay, so it has different penalization and this penalization and is asymmetric. Okay, so you expect to see a good mean p-bar loss. You expect to see this curve, like the slope of a pinball, for example. Okay. The other metric that we are using a lot is the reliability deviation, and this is we want to assess how reliable is our model. So we want the model to predict the same probability as the actuals all the time in different probability levels. Okay, and as you can see, the top performing models at the moment is the mixture model with boosting algorithms, and of course the lasso, the penalized quantile regression. And I'm not surprised, but from the fixed variation models that they cannot account the variation in probability levels in intermediate quantiles, as you can see here and here. Okay, I'm speaking about the LR lasso and MM lasso. So this is about the price model, what we did so far, and I'm still working on that to improve our forecast, of course. The other model that I'm presenting you today is the wind to power model that we created. And here you can see a map of the wind farm that we have in the Great Britain at the moment. Okay, and we used all these wind farms for the wind power model. So this is the pipeline of the wind power model. So I will be very brief on that, and we are including wind speed forecasts with horizon up to 2 days ahead with base times. Base time is the time that we're releasing the forecast. Okay, so this is what I need to make a comment on that. This is not exact at the times because the ECMWF they have these base times, but they have like 5 hours, 6 hours lag to release that due to technical, they need to fit the models and they need to produce the forecast, but the actual times are those. So we have wind speed forecast with horizon 2, base times 0 and 12, 1 hour resolution, the granularity is this. And we have wind speed forecast same, 2 days ahead, base times 6, 6 in the morning and 6 in the afternoon with 3 hours resolution. So the second step is that we interpolate the wind speed forecast to every wind farm, okay, known till 2023. And then we are using a power law to extrapolate the wind speeds to the wind farm's hub height. Of course, you can understand that we are using data from manufacturers here because we know the models of the turbines that all these wind farms have. So we want the hub height, first of all. And of course, we need to know the number of turbines that we have in every wind farm, okay? In order to create the power curve for those that are familiar with the wind power, okay? So a lot of data together again. So we are using the power law to extrapolate the wind speed heights to the farm's hub height. And then you do this for one turbine, but what if you have like 10 in the wind farm? And 10 the wind turbines, they can be dispersed in different ways. You don't know why. So we use a Gaussian filter to produce a smooth power curve for all that accounts for all the wind farm. Okay. And also, the extra step on that is that we apply the bias correction as well. Okay. We did this for every individual wind farm. Okay. We converted the wind speeds to wind power, because we constructed all the wind power curves for every wind farm. And then we aggregate those in order to have the deterministic forecast for the national level. We aggregate those, all of them. Okay? And the same goes, base times, the same all the time that we have this wind speed forecast. And here's most, it's limited, the methodology that we used, the model selection that we used, because already we had good models. So in forecasting, we don't want to explore many things. If we have something that beats a state of the art, we stay on that, and we don't want to go further, something like that. Yeah, we compare a lot of methods, yeah, but believe me, especially in industry, they don't want very complex things in the end. So here we are following again the same framework, non-parametric and parametric ways. Okay, so we assume that our predicted distribution of the wind power generation forecast, they follow a gamma distribution or a power exponential. Okay, but we are use gradient boosting traits as well here, and when comparing with the same way. And as you can see, the gamma and the power exponential of the parametric ways, they beat the boosting trees for a bit. And here you can see the power exponential buds and what this buds means. So in forecasting, the correct way, it's the most efficient way to produce a very reliable and good forecast to do what we say online forecasting. So we have a pre-trained model, and you're forecasting every day or every certain period or every month. In my case, I did a batch forecasting, so I'm updating my model and produce forecasts, adding 1 month all the time, like an expanding window, and produce forecasts for the rest of the year. Okay? So I neglect to tell that all the time because you probably know that we are students, we're doing a PhD, so we don't have million resources to do, very detailed forecasting or predicting models. Okay, so along with these resources, I try to adapt and I adjust the batches as well. Okay, so as you can see, the parametric method, the PA batch, is a very good at the moment. And why the parametric method? Because parametric methods are very easy to be trained, very fast compared to the boosting algorithms, okay, or even deep learning methods. When we produced the probabilistic forecast for the wind power generation, we said, okay, we need to see if there is an actual connection between the price and the price spread. Okay, so here, the first step what I did is to explore the Spearman correlation between the price spread and the wind. Not the wind actually, is the difference with the day ahead and the closest wind power forecast. So as I said, we have different lead times. Yeah, thank you. We have different times in the wind power forecast. So we're going to incorporate this update on the wind power forecast as a difference between the day ahead and the closest wind power forecast that we have on the settlement period that we are forecasting with the actual price spread. So we have a correlation table here. We said, okay, yeah, that's quite intriguing, but does not help us a lot to understand what is the relationship between those two. So then, I fit a random forest model, a very simple random forest model, okay? With predictors, I have the price spread, of course, as a target. And as predictors, I have this update on the wind power forecast, the demand error, and I included a white noise, a picture with white noise in my model, okay? And I extracted the partial dependence for each feature in order to see what is going on with these features. Do we have a case here with the wind power forecast or not? So I found out that I have a non-linear relationship between the price spread and the update of my forecast. Okay, I have the demand error is something that I expected to happen. Okay, and of course, I was anticipating to see the white noise like that to be kind of stable. Okay, we have a bias. I know it's not a predictive model, just to derive the partial dependence, but if you want to see, if you see some hiccups in the white noise, so you definitely don't see actual results in the partial dependence. You see that your model is picking white noise in the end. So we're currently at this stage that we saw that there is a non-linear relationship, okay? And if you want me to be more detailed, and I'm finishing 2 minutes, that you see some steps here. It's like a step function here. So in my mind, as a forecasting the future, I'm just looking different regimes in different power levels here, megawatt hours here in the x-axis. But this is something that I need to explore in the future. And then we took all the price forecast, of course, and the wind power forecast. And if you're using the probability integral transform of the price forecast and the wind power forecast, you can create an empirical copula that copula can show you the actual dependence that you have between two forecasts, two probabilistic forecasts, in different probability levels. And this is something that I was anticipating to see as well. So you see increased relationship in the tails between those two variables, but in the corners. And why is that? You have different bands here. Is when the system is in different states, the deficit and the surplus. Okay, see the densities here in different lead types. Okay, so this is the last step, and I'm thinking to fit a model, a copula on that, and see how it goes. You draw samples and see measure KL, Kendall style or other metrics that we are using in the copulas. I'm thinking about causal forecasting as well. See if it's working, because in the electricity markets you have this causal behavior that you have increased wind, you have price drop, and other causal effects as well. Yeah. So yeah, I'm thinking a lot. Also, I'm thinking Bayesian approaches as well. I have other slides if you want to ask me something specific about my models in the appendix. And thank you very much.